Hi guys, nice to see you back. The plan for today. We're going to identify the anode and the cathode of the light emitting diodes. And then we're going to build our first testing circuit for LEDs. Let's start it. As you know very well, the diodes, they don't conduct in both directions. They only conduct in one direction because they are electronic switches. For instance, if I'm using my meter to energize this diode and I just touch the terminals, you won't see anything right now because the diode does not emit light. But if I turn it the other way, now you can see the diode blinking, okay? So it does not conduct in both directions. Like in this direction, if I energize, it's not conducting. Why? Because the red of the meter is touching the cathode of the diode, and the black of the meter is touching the anode of the diode. So the diode has a polarity. It has to be aligned with the anode to the red and with the cathode to the black. So that's the first thing to do for today, how to identify the terminals. It's very easy if you think about the rectifiers. Because on the black body of any rectifier, there is a silver ring. This one is identifying the cathode. So I have them again right here. And these ones, I have 3 of them here. You can clearly see the silver ring identifying the cathode. Now for the LEDs, like this one here, there is no place on the body to draw the silver ring. So now, take a look. If we go on the net and we just type light emitting diode, you go on Wikipedia, and one of the first pictures appearing is that one here. So I have a magnified picture representing exactly this one. So far so good? So now, I'm writing here several methods to identify the anode and the cathode. Now for the LEDs. You find these things described not only in Wikipedia, but also in a lot of magazines and even manuals. Take a look. First thing they say, I say here method number 1. Okay? For the method number 1, they say longer terminal is the anode. So shorter terminal is the cathode. It says right here, if you allow me to just see, the cathode is shorter and the anode is longer. However, you are going to be in the situation to compare different kinds of diodes, and then you're going to find out that it's very difficult to figure out actually what terminal is longer and what terminal is shorter. So this method here, I put here some question marks, okay? What if you have to try to measure a diode which is extracted from a printed board? The terminals are already cut, so they are equal size, both. Number 2. They also say, hey, look inside the diode body and you're going to find out that one of the terminals suddenly becomes larger. Why does it become larger? Because this one here is also used as a anvil, as a support for the actual semiconductor, because the semiconductor is only this yellow little spot right here. That's the whole semiconductor. The rest supports for the terminals and the body used as a prism to spread the light out. So they say again, look inside the body, and the larger terminal is the cathode. If you're lucky, I'm gonna show this to you. If you're lucky and having a transparent body, then they are perfectly right. The larger terminal is on the right, so this is gonna be the cathode. And the other one is a bit narrower, this is gonna be the anode. So far so good. However, what about this one? The body is not transparent, it's semi-transparent. So not easy at all to identify what terminal is larger. And then take a look at this one here, similar, which is a diode, an LED, designed on purpose to replace the light bulbs. The body for this one is not transparent at all. And what if the diode is this size, which is only 3 millimeter diameter? So this thing about, take a look at the terminals and the larger one is the cathode, I put a big question mark here. So, larger terminal is the cathode. I'm gonna put 2 question marks, okay? Why is this again? Because only in special situations you should be able to identify the terminal representing the cathode. Method number 3. They say here, hey, on the circular end of the body for the diode, there is a flat spot. And that flat spot is identifying the cathode. So I'm gonna find such a diode for you right now. You won't be able to see it properly from a distance. But here, on the right side, there is a little flat spot on the diode body. And yes, this one is representing the cathode. Similarly, if I'm looking for another one, similarly here, this one also has a flat spot right here on the right side, a flat spot representing the cathode. But if you pick up any of these 10 millimeter diodes, the biggest ones for common use, these ones, if you take a look at them, they have no flat spot. So this method is not very reliable as well, because even big diodes like 10 millimeter diameter, they have no flat spot. And what if you have a 3 millimeter diode or even a 2 millimeter diode? It's practically impossible to identify a flat spot. So I write it here. The flat spot is representing the cathode. What these 3 methods they have in common? They have something in common though. All of them here are visual. What does it mean, visual methods? It's for lazy people, you don't take any measurement. So by just taking a look at the diode, you should be able to identify the anode and the cathode. What I'm telling you is, do yourself a big favor, forget about these methods, all of them being visual, and let's pass to the next one. Use a DMM, a digital multimeter. Now, we're gonna have a problem as well. I'm gonna use a multimeter. This one here, it's a good quality multimeter. And all the multimeters regardless the quality, regardless the price, they have a position somewhere around the rotary switch, like this one here with the symbol of a diode. So you put your meter on that position, so not on ohms, on the position representing the diode, and then you try to measure them. But what the manufacturers of these meters won't tell you is that the symbol here of the diode is actually intended to measure the rectifiers. And any rectifier you measure with any meter, it doesn't matter how cheap it is. You can even find meters on the market which are $10. All of them are measuring very nicely the rectifiers. But that position of the diode on the multimeter, it's not designed for LEDs. So what happens is there are some multimeters having the power supply inside 3 volts. With these ones, you almost never be able to find the diode conducting or not conducting, and I'm talking about the LEDs. Only about the rectifiers, but not the LEDs. So if I'm using the multimeter on that position here, on some diodes it's going to work fine, like on this one here. On some of them it's going to work fine. But on some others, it's going to work a bit less. Let's just try some other diodes. You see on this one here? You won't be able to identify the light on the diode. You can barely see something, okay? Even very good quality meters like this one are having trouble to identify the anode and the cathode because that position for the diodes, again, it was actually designed for rectifiers, not for LEDs. So guess what? Older meters are better, because for the new meters, what's the reason why you can't see the light on some diodes? Is because all the meters, the new ones especially, they were designed with power saving in mind. So the current inside the diode is so low that the diode won't be able to emit the light. All the meters are better, because 20, 30 years ago, the manufacturers wouldn't care much about the consumption from the battery. And the best meters, if you want, are 2 of them. Either the old ones with a needle or the bench multimeters. With the bench multimeters, you should have no problems to identify. Like here, I'm going to use one of them. And if I'm using one bench multimeter, I should have no problems to see the light on any such diode. So, as you can see on this one, it's very easy to check. I'm going to pick up a blue one. One direction it does not conduct. The other one should conduct. You can see the blue light. See? So with this one, you actually have no problems at all to identify, because the bench multimeters, they don't have this problem of saving energy. Okay? The problem you have is with the portable multimeters. These ones have a problem. Okay? Now, I'm writing here the method anyway, because this is much better anyway. And now I'm going to pass to the number 5. With this one, you cannot fail. With this one, you can identify the diode anytime you want. So, put the diode, the LED, in a test circuit. This is what we should do. And now we're going to make together the simplest possible testing circuit for a diode. Take a look what you need. I'm going to pick up a 9-volt battery connector. Is this one here. This is what I found in my junk box. And I'm going to pick up another kind of connector, which is a conversion from the jack to 2 pins. And I'm going to use this one. So far, so good. If you go right here and you look for 9-volt battery connector to 2 pin, here you have both these things together. Don't look at the price because the price looks like almost $14. You don't need to buy all of them, but here is 10 pieces, okay? So 10 pieces. Now, what is the trick about that? Don't connect here a battery to measure directly the LED, because you're going to keep burning LEDs one after other. Remember that for any diode, it doesn't matter what kind, you need a limiting resistor. And I started to build actually using the same kind of connector, and I stopped because I realized I want you to see how it is done. So what I did, I actually cut the red wire somewhere here. Please don't cut it in the middle. Cut it somewhere higher, closer to the connector of 9-volt battery. You solder on the way, on the two ends of the cut red wire, a 1 kilo ohm resistor. I'm going to explain you later on why 1 kilo ohm resistor. It can be anything between 1 to 2 kilo ohms. And before I solder the other side, I have to insert on the wire a shrinking tube. So this is why I didn't cut it in the middle, because I want to have enough room for the shrinking tube. Okay. So now I'm going to just solder the other side. It's going to only take 1 minute. Okay. Okay, we solder the other side. So now, once the two legs are soldered, then I pass the shrinking tube over it. And this is why it's called shrinking tube, because I'm going to put the hot iron tip over it. So the tube is going to shrink down, because I don't want accidental touch over the soldered terminal, the two terminals of the resistor. Okay, it's good enough. So now, it looks similar to the original, but it's actually not the same, because the trick is somewhere on the red wire I connected 1 kilo ohm resistor. So now, I pick up a 9-volt battery. I connected it over here. And I plug the other connector with the 2 pins. And now on these 2 pins, I can check any LED I have in my collection. You see this? It's a blue one. You can see the light. If you put it the reverse way, it won't conduct like any diode. Okay? But you can check and identify the diode right away, and also if it is good or not. This was a blue one. This one here, I simply don't care what terminal is longer, what terminal is shorter. Okay? I can find out right away which is which. I pick up another one. That's an amber one. If you put it reverse way, nothing is going to happen. And I pick up another one. You see, a green one. So you can check all of them anytime you want. It's the easiest tester you can build, okay? And by the way, where is the anode and where is the cathode? while you are energizing the LED, you are going to notice on the connector that here in the top is a negative sign and here is a positive. This is why I chose that particular connector. The negative means the pin of the diode connected to it is the cathode, and the positive is that the anode is connected to it. That's how you know the polarity. So don't forget, all diodes, they need what? They need a limiting resistor inside just to make sure you won't burn out the LED. And now, last thing I'm showing you, if I get rid of this little vise, what I have here is a LED replacing a standard light bulb, and this is supposed to work at 12 volt. What do you think is inside? Of course, it's the LED. But because you're going to connect it to a power source, guess what? Inside, you're going to have a resistor. So, you're going to have a resistor. I have here a power supply. Right now is 9 volt energized. And if I'm bringing here closer a multimeter, it doesn't matter, it's an old one. You put it on 400 milliamps, and then you put it on milliamps, and then we make some connection. Meter is off. You put the meter in series with the diode. So from here, we pick up the other leg of the diode, okay, and you link the other leg of the meter to the power supply. And with the power on. You see? Is the red light. What you can read here, though, is the amperage passing through the diode right now. 11.8 milliamps is like 12 milliamps, but this was intended for 12 volt. I prefer to energize at 9 because it becomes too bright. However, if I'm going to 12 volt, take a look what happens. So the current goes approximately to 17 milliamps, okay? What does it mean? From the power supply, remember, the power supply voltage equals the voltage across the LED plus the voltage across the resistor. So guess what? Inside the socket, this is a bayonet socket, they have a resistor inside. Because otherwise, in the absence of that resistor, the diode is going to burn out. So if I notice this was a red LED and the power supply was 12 volt, remember for the red, green, amber, yellow, we use for the calculation the value of 2 volts. So if the voltage is 12, I have 2 volts across the LED. The voltage of the resistor is going to be 12 volts minus 2, 10 volt. So this is the dropping across the resistor. I know the amperage, it was 17 milliamps. The current was 17 milliamps. So guess what? Instead of 10 volts, if I write here 10,000 millivolts, I'm going to divide 10,000 millivolts by 17 milliamps. Milli and milli, they disappear. Volt over amps, I'm going to get the value directly in ohms. So, if you want to do this calculation, it's going to take only seconds. Take a look. 10,000 millivolts divided by 17 milliamps. So, that's what you have inside. Again, 10,000 millivolts divided by 17 milliamps. you have approximately 600 ohms. That's the resistor inside. I'm going to disconnect this one. Remember, this is a bayonet diode. And now I'm picking up another one intended for the same purpose, to replace a 12-volt light bulb, incandescent bulb. But this one comes on an Edison socket. It's not bayonet, it's Edison socket. Also 12 volt. So I do the same. I connect one leg and the other one. And when I put the power on, oh, this is a white diode. Take a look, what is the amperage? It's exactly the same, 17 milliamps. So, remember, 17 milliamps. We do the same calculation. Voltage of the power supply is the voltage across the LED plus the voltage across the resistor inside the socket. 12 volt equals, hey, this is a white LED. For the white and blue LED, we use 3 volts instead of 2. So the voltage across the resistor is going to be 9 volt. So this time, if I want to find the resistor, I'm going to convert 9 volt into millivolts, 9,000 millivolts, over the same 17 milliamps. Milli and milli disappear, and volt over amps, I'm going to get the answer directly in ohms. So if we quickly do this calculation, what's going to happen is going to have 9,000 millivolts divided by 17. You have 530 ohms inside the socket. So that's the conclusion for today. The size of the resistor is made in such a way that the current absorbed by the LED divided into the voltage is going to give you the size of the resistor inside. Okay? And this is the simplest possible testing circuit we built by just soldering one resistor in series with our battery connector. Again, one more time to energize, you see? And next time we're going to build more sophisticated testers. Going more in depth is going to be the last step before we go for what we actually want, the 7-segment displays. Thank you very much. See you next time. Bye-bye.